In this video, we'll work through some examples of even and odd functions. So we'll go through a reminder of the definition of what an even and odd function is. We'll prove if a function is even or odd algebraically, and we'll prove whether a function is even or odd graphically. So recall that an even or odd function is defined as follows. Let f be a function and D the domain of f. F is even if f of negative x equals f of x for all x in D. F is odd if f of negative x equals negative f of x for all x in D. Even functions have symmetry about the y-axis. Odd functions have symmetry about the origin. So to begin, let's determine whether the following functions are even, odd, or neither even or odd. So we haven't talked really about when a function is neither even or odd, but it should be relatively intuitive, right? If it's not even, if it doesn't satisfy the condition that f of negative x equals f of x, and it doesn't satisfy the condition that f of negative x equals negative f of x, then it would be neither even or odd. So for this first one, we take negative x and plug it into x to the fifth plus x. So we get negative x to the fifth plus negative x. And negative x to the fifth is negative x to the fifth. And then plus negative x is minus x. So we get a negative x to the fifth minus x. And if we factor a negative out of the entire expression, we'll have negative x to the fifth plus x. And this is our original function. And this is our original function. So we could just say equals negative f of x. So this shows us that f of x is odd, since it clearly satisfies the condition that f of negative x equals negative f of x. Let's do another one. Suppose we have g of x equals 1 minus x to the fourth. So we'll follow the same procedure. We'll plug in a negative x. So we'll have 1 minus negative x to the fourth, and 1 minus negative x to the fourth is just x to the fourth, right? So we have 1 minus x to the fourth, and this is the same thing as our original function, g of x. So since g of negative x equals g of x, this implies that g is even, since we satisfy the condition that g of negative x equals g of x. I've got one more for you. H of x equals 2x minus x squared. So like we did before, we'll follow the procedure of plugging in a negative x into h, since that's our test. And then we'll have 2 times negative x minus negative x squared. 2 times negative x is negative 2x, and negative x quantity squared is x squared. And this looks like we might have a problem, because if we factor out a negative, we have 2x plus x squared, and this is not our original function, nor is negative 2x minus x squared. So since we don't satisfy the conditions that h of negative x equals h of x for it to be even, or h of negative x equals negative h of x for it to be odd, h is neither even nor odd. For our last example, we'll take a look at finding out if a function is even or odd by inspection of its graph. Determine whether the graph of the function below is even, odd, or neither. So remember that an even function has symmetry about the y-axis and odd functions have symmetry about the origin. That is, if we look at all of the y values on the positive x half, that is, if we look at all the y values on the positive half of the x-axis, those should be the opposite sign of the y values of the function on the negative half of the x-axis. And by inspection, these two y values look to be opposites, as well as these two here. And it generally follows the same shape. Now, in general, we'll be giving more specific graphs than this. This is just kind of drawn up graph that I put together. But you can tell by inspection that since this has symmetry about the origin, f is odd. Since it has symmetry about the origin.